Welcome to Module 5, which is on mass transfer. Mass transfer is of key importance for chemical engineering, and it's no different for electrochemical engineering. Since this is the first screencast of this module, I will start by discussing the learning goals. You can see them here, so you should be able to explain why mass transport is important. You should be able to understand the differences between the modes of mass transport, and you should be able to use mass transport correlations to calculate limiting current densities for different electrochemical cells. In this first screencast on mass transfer, we will discuss its importance. Before going into the content, I would recommend you to carry out quiz question 5.1 to already familiarize yourself a bit with mass transfer. Let's start by a general introduction of mass transfer in electrochemistry. And we do this by this scheme here, this example, where we see an electrode and we see here the concentrations of iron 2 and iron 3. Now, if there's no reaction at the electrode, then, well, there's no concentration difference between the situation at the electrode and in the bulk. But now we lower the potential. If we lower the potential, then iron 3 starts to be reduced to iron 2. And this is what happens because the iron 3 at the electrode is consumed and iron 2 is formed. So that results in concentration changes. And that's what you see here. Now, in principle, if there would be no mass transfer, then the reaction would quickly stop because iron 3 at the electrode could have completely disappeared and the reaction would stop. But now mass transfer kicks in. Mass transfer is the process which makes sure that iron 3 from the bulk moves towards the electrode. And at the same time, iron 2 that is produced at the electrode moves away from the electrode to the bulk. Now, so the extent of this mass transport is determined by different modes of mass transfer, which we will discuss in this module. Now, why is this mass transfer important? As you probably remember, in the previous module I said that the most important figure of merit for an electrochemical process is the cell potential. And here you again see the equation and the figure I showed you before. So the equation contains the equilibrium potentials, the overpotentials, and the ohmic contributors. Now, where does mass transfer kick in? It especially applies here to the overpotentials, because the overpotentials indicate the reaction rate, and the reaction rate depends on the concentration at the electrode. So if the concentration at the electrode is lower, it reduces the reaction rate, and in turn it results in an increase in the overpotential. And this increase we call the so-called concentration overpotential. This is really the most important contributor of mass transport in the cell potential. Another, maybe somewhat less important contributor of the mass transfer can be in the ohmic drops, because you can get into a situation where you really deplete your electrons near the electrode, and that then results in a lower conductivity near the electrode and hence a higher ohmic resistance. But the focus in the discussion here will be mostly on this first part with the overpotentials. Mass transfer can not only influence the cell potential but also the selectivity of a reaction. And by influencing the selectivity, it affects the current efficiency of that reaction. Let me show that with an example. Here we have an electrode an anode on which either chlorine evolution or oxygen evolution takes place. Now let's look first at the situation without any mass transfer limitations. Then we can assume for a typical chloralkali process that the concentration of the chloride is 5 molar. Now using the exchange current density and the Tafel slope, we can calculate what the corresponding overpotential is at a certain current density, namely 77 millivolt. And based on the kinetics of the oxygen evolution, we can calculate that that corresponds to an oxygen formation of 1%. So, which means we get 90% chlorine and 1% for the oxygen evolution. Now, if we would have a very big mass transfer issue, it would mean that the concentration of the chloride near the electrode would dramatically drop to, say, for example, 0.05 molar. Then, with using the same numbers for the exchange current density and the Tafel slope, you can calculate that the overpotential you need to achieve a current density of 6 Ka per square meter is 137 millivolts. Now, assuming that the oxygen evolution is not so much affected by the mass transfer, which can be defended because oxygen evolution depends on the amount of water, and you always have water, this means that the resulting the amount of oxygen that is formed is 3.2%. So now the current efficiency for chlorine evolution has dropped from 99% to only 97%. Now, I can imagine that this is a bit complex. I would recommend you to carry out exercise 4.4 from the previous module, because this will really help in understanding this example. Also, I recommend you now to carry out quiz question 5.2. An important concept in mass transfer in electrochemical systems is the limiting current density. What does that mean? It basically means that the concentration of the reactant at the electrode becomes almost zero. So for our example, we get to that situation when the iron 3 concentration is nearly zero. And it basically means that the reaction at the electrode is very fast and that the reaction is limited by the mass transfer from solution. You can also see that here with the equations. So we have the mass transfer from solution driven by the concentration difference, and also, of course, the mass transfer coefficient, KL. And you can see that this reaches a certain maximum value, because if Cs is 0, you cannot make the mass transfer even bigger. So this is kind of independent of potential. On the other hand, the kinetic term is driven by the concentration, also by the concentration at the surface, but also by the reaction rate. And this reaction rate is highly potential dependent. So the higher we make our overpotential, the higher our reaction rate constant. So what does that mean? At the limiting current density, basically we have a very high reaction rate constant, which means we have a very low concentration at the surface, and the mass transfer is really driven, the mass transfer really determines the rate of the reaction. You can also see that here in this graph on the right, where we see the reaction rate or the current density as a function of the potential. What do we now see? If we're at the equilibrium potential, of course, there's no net current. If we then increase the potential, the first thing we see is that we get a faster reaction rate, a higher current density. Why is that? Because then our kinetics are improving. We increase the potential, so we have a higher overpotential, hence according to the Butler-Volmer equation, faster reaction kinetics. But we reach a certain point where this starts leveling off. And this is basically the point where the concentration near the electrode starts becoming zero. And if you then increase the potential further, basically nothing happens anymore to the reaction rate. It remains constant. And that is because this mass transfer term is a constant value. It's not increased anymore. So even though at the same time the Kr is increasing further and further, it also means that the Cs, concentration at the surface, is dropping further and further. And it's not exactly zero, but it's more 10 to the minus 6, and then it drops to 10 to the minus 7, and 10 to the minus 8, and 10 to the minus 9, 10 to the minus 10. So it really becomes very, very small, and this basically means that your reaction is limited by mass transfer from solution. Obviously, we see the same for the backward reaction. So this is the concept of limiting current density. Now, what are the modes of mass transport? There are three for electrochemical systems, namely diffusion, which results from a concentration difference. So if you have a lot of iron 3 here and you have little iron 3 at the electrode, then the iron 3 wants to move that way. Then there's convection, basically a movement as a result of a mechanical force, for example, from steering. So the steering brings the iron 3 from the bulk to the electrode. And then the last possibility is migration. Migration is the transport of ions as a result of a potential difference. So basically, if you have a negative electrode, then positive ions want to move towards that electrode, whereas negative ions are pushed away from that electrode. And now, migration is unique for electrochemical systems. So diffusion and convection, you have that in any chemical reactor, but migration is really something that's unique for electrochemical systems and can make the description of mass transport in electrochemical systems a bit more complex than in normal chemical reactors. You can also describe these modes of mass transport with an equation, namely the Nernst-Planck equation. You can see it here. The flux of a component depends on a migration force, a diffusion force, and a convection force. And here you see them with their respective units. Now, basically, Nernst-Planck equation is just an extension of Fick's law of diffusion, but now also includes this migration term. The flux that is here, that is directly related to the current density via the number of electrons and the Faraday constant. One big limitation of the Nernst-Planck equation is that it's only valid for relatively dilute systems where ion-ion concentrations can be neglected. And this is a major limitation because typically electrochemical systems are not dilute. Typically we have a lot of ions, so this makes the validity of this Nernst-Planck equation less. Later, in one of the following screencasts, we will briefly discuss an alternative.